Hi, my name is Ioni Lisha, and this is a video for the Molecular Biology class, MCDB 427 at the University of Michigan. Today we'll be talking about the logic behind Table 18.2 from Robert Weaver's Molecular Biology book. This is Table 18.2, which we will be coming back to shortly. The main idea behind Table 18.2 is the three-site model of the ribosome. Here we can see the E site, the P site, and the A site. Now, with previous studies done with pyrimycin, it was already known about the existence of the A site and the P site. This is pyrimycin, and it kind of looks like a tRNA. It has this part right here that is an amino acid, and the modified adenine. The adenine is modified at this nitrogen right here by a dimethylation. It is often said that pyrimycin most closely resembles tyrosine-tRNA. The main difference being that tyrosine-tRNA does still have its tRNA part, whereas pyrimycin has that replaced by an OH. Now, Table 18.2 comes from a study, 3 tRNA binding sites on Escherichia coli ribosomes by Reinberger, Steinbach, and Knott-Niehaus. What the researchers did is that they found evidence for a third site, which they called the E site. E meaning exit. We'll be talking about that later. What the researchers did is that they created 3 radioactive tRNA constructs. The first construct used uncharged tRNA. So, this tRNA is supposed to be charged with phenylalanine, but it simply lacks that phenylalanine. So, again, this is just an uncharged tRNA which lacks its phenylalanine. The second construct is a phenylalenyl tRNA. So, this tRNA is just like the previous tRNA, but in our case, it is charged with its amino acid, phenylalanine. The third construct is kind of special because not only it had phenylalanine on the tRNA, but it also, the phenylalanine was acetylated. So this kind of was behaving like this tRNA had not only one amino acid on it, but an acetyl group which acted as a second amino acid. So the idea behind this construct was that it was supposed to be an analog of a dipeptide charged in a tRNA. Now, the researchers ran 2 types of scenarios. The first type of scenario included ribosomes, which had a poly-U mRNA included with them. And the reason why they used poly-U is because it was already known, based on studies done a long time ago, that UUU codes for phenylalanine. So uracil, 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 triple uracil codes for phenylalanine. The second type of construct included just the ribosome. It didn't have any mRNA. And the researchers' strategy? Well, their strategy was to measure the number of tRNA molecules, so, these tRNA molecules that they created, bound per 70S ribosome. And I say 70S because they got the ribosomes from E. coli. To measure the binding of tRNA to the ribosome, they used a simple filter binding assay. Now, the main idea behind the filter binding assay is that tRNA, unlike other single-stranded RNAs, does not bind to a nitrocellulose filter. So here in yellow, we can see the nitrocellulose filter, and if we have tRNA here in the solution and we pour it through the nitrocellulose filter, it would not stick. It will instead flow through and it will be in the filtrate. Ribosomes, on the other hand, which contain proteins, will stick to the nitrocellulose filter. So if we have ribosomes and we run them through a nitrocellulose filter, they will stick to the filter. Now, lucky for us, if it happens that the tRNAs bind to the ribosome, and because the ribosome binds to the filter, the tRNA will also be bound to the filter through the ribosomes. So, if we have a solution which has tRNAs bound to the ribosomes, and we run that solution through a filtrate, tRNAs will bind to the nitrocellulose filter. And if we take this filter and we put it under a Geiger meter or a radioactive scintillation counting instrument, we will see that this will light up, which shows that there will be radioactive here. Again, let me reiterate, the tRNAs we made were radioactive, and that's why we will see radioactivity. So now that we talked about all of that, we can take a look at some of the researchers' data. The problem is that here, what we see in figure 1 has a lot more information that we're going to cover in this video. So I went ahead and simplified this figure. Okay, so here we are, much better. So what the researchers were showing here in the y-axis is the number of tRNAs bound per each ribosome. So for each ribosome, we see how many tRNAs bound. On the x-axis, on the other hand, we can see how much of that acetylated phenylalanine tRNA was used. So the more we go to the right, the more the concentration of acetylated phenylalanine tRNA increases. What we can see here is that as the concentration of acetylated phenylalanine tRNA increases, the amount of tRNAs bound per ribosome also increases. So in this part right here, we can see the amount of tRNA bound per ribosome increasing. But then, once we reach a certain value, we can see that the amount of tRNAs bound per ribosome kind of plateaus at around a value of 1. And this led the researchers to conclude that, once you reach a certain value of acetylated phenylalanine tRNA, only one acetylated phenylalanine tRNA will bind per ribosome. Now that we talked about that and you got sort of a flavor of the data in the research paper, I will go to the table itself. What the researchers saw is that the acetylated phenylalanine tRNA, as we said previously and as we saw previously in figure 1, binds only once when we provide poly-U, right? That's what we saw before. And they found out that it binds either in the P site or in the A site. Phenylalanine tRNA, on the other hand, binds twice if we provide the poly-U mRNA, it binds twice, and that binding can be both in the P site and in the A site at the same time, whereas with acetylated phenylalanine tRNA, it goes only once, and it could be either in the P site or the A site. And now, drum roll please. When you take uncharged tRNA and you provide poly-U mRNA to the ribosome, that uncharged tRNA binds to the ribosome not once, not twice, but 3 times. And this was pretty fascinating results. And the researchers found out that the tRNA bound in the P site and in the A site. And the reason why these results were fascinating is because this was clear evidence for the existence of a third site, which they called the E site. And again, E was for exit. They also found out that if you don't give the poly-U mRNA to the ribosome, uncharged tRNA binds only once, and it's in the P site. Phenylated tRNA doesn't bind at all. And acetylated phenylalanine tRNA binds only once, and so like before, it binds only once, but this time it's only in the P site. But actually, these last results were not from the researchers themselves. This was previously known, and this was from a previous study. So now that we said all of that, now we can talk about some of the major conclusions that we can draw from this study. The first one, and the most important conclusion, is that there is a new tRNA binding site called the E site. And again, like I previously said 2 other times, it's called E site for exit, as the researchers believe that this site can only bind uncharged tRNA. And they believed that this meant that this site bound the tRNA after it had released its amino acid. and it bound this site before it left the ribosome, so E for exit. Another fascinating result is that only acetylated phenylalanine tRNA can bind. And to the researchers, this could possibly show that only one polypeptide chain can bind to the ribosome. And again, it's fascinating that this binding could be either in the A site or the B site. This model sort of agrees with information that only one polypeptide chain is produced from a ribosome at a given time, right? It's not like the ribosome holds two polypeptide chains at the same time. A third major conclusion was that not all binding sites are the same. And for example, one example we can give is that 2-amino-acyl tRNAs, right? So as we saw here, 2-amino-acyl tRNAs could bind at the same time, right? In this case right here we saw that. But only one acetylated tRNA can bind at the same time. And then if we have this case right here where we have uncharged tRNA, it can bind 3 times, and it can bind in a new site called the E site. So this clearly shows that the P site, the E site, and the A site are different. And a final conclusion is that mRNA is needed for both E site and A site binding. So when we looked at these 3 cases right here, when we only had tRNAs but we didn't have mRNA, there was no E site or A site binding. So it seems like mRNA is helping the ribosome create those E and A sites, or it's crucial for E site and A site binding. And most importantly, out of these conclusions is the fact that we need the mRNA for A site binding, because as we know now, A site binding is the site where the amino-acylated tRNA first enters the ribosome. And so this site is important for tRNA recognition. So if the ribosome doesn't have the mRNA, of course it's not sort of unexpected, now that we know all of this, that once we don't have mRNA, we won't have A site binding, because there will be nothing there to recognize the incoming tRNAs. That is it, folks. Thanks for watching, and go blue!